that Godsey's experiment itself showing a rather quick, quote unquote, quick time response between excess heat production, observation, helium, is basically saying that you can argue that the helium has to be born something like 1,000 angstroms, at most a few thousand angstroms from the surface. Otherwise, you wouldn't have seen the helium. You can make similar arguments based on this about the fraction of helium that's hiding out. Namely, if you go in a micron, you say helium's sort of a micron in, and you get a characteristic time, you find at the end of the calculation that only a little bit of helium comes out, and most of it's still stuck in your cathode. You didn't get it out.
So what is it that is sort of pushing the helium to try to get out?
Nothing forces it. Or on the other hand, maybe I should quote Onsager. Well, of course, it's the force from chemical potential. It's Onsager force, but basically it's just a diffusion calculation. If it were in infinite space, you have it localized, it would melt and spread out. On the other hand, if you have a boundary where it can leave, then it melts and spreads out, but then it gets sucked out from the surface of the boundary. Before the takeaway message, I want to talk a little bit about localization. There's been a lot of interest in nanomaterial. And in nanomaterial, at a small spatial scale, I want to think a little bit about this problem. Suppose you get excess heat. You're building up helium, and the helium's plugging up your vacancies, your active sites. Now you're going to try to get rid of it. Well, imagine that you have a big sample, and you got helium somewhere near your surface, and you're trying to get the helium out. Contrast this with the sample that looks like this, where you have little islands of palladium in a material with low background electron density, so that helium can leak out. Now your problem of getting helium to leak out, your helium in a nanomaterial can get out much faster. In fact, it gets out much faster. Scales like square of the radius or square of the characteristic distance or something. Anyway, so the thought being, if helium diffusion is limiting the excess power, then under those conditions you would expect the excess power to depend on temperature, the way we've reported that storm sees the flush and plot sees. Now, not everybody sees that. At SRI, they don't see the temperature dependence. In their experiments, they raise the temperature, but their excess power doesn't go correspondingly. So the argument is that in the SRI experiments, they're not running sort of all out. Namely, they're not being limited by the helium plugging up their active sites. So that would be why there'd be no temperature dependence. So correspondingly, the argument is that this temperature dependency would only be seen in cells where you're making so much helium that you plug up your active site, and it's actually limiting the amount of excess heat you've got. And then if you've got a nanomaterial where you've got nanoscale samples, now you can get rid of your excess heat for your helium much, much faster. And the argument then is that the power per unit volume of palladium in a nano configuration would be very much larger. So to follow up on that, what you would like is you'd like an experiment. Ideally, here's my wish list. Mitchell always tells me, says, what kind of experiment can I do? What kind of experiment can I do? Here's what kind of experiment can I do. If you have a picture like this, it would be fun to build, say, 4 or 5 of these things where their characteristic size of the island was known to be relatively uniform, and that we could plot the maximum excess power per unit volume on a plot with characteristic size of the islands. So then, under the assumption that's working really well, that we're being plugged up by the helium, then we would be able to see whether the dependence on diffusion size is correct. And then to back that up, we actually actually want a 2D set of measurements. You'd like to do it at different temperatures. With the different temperatures, you get different helium diffusion coefficients. So if you have those spatial scale and temperature, you'd be able to prove that this is what's limiting. But I contend, I want to make up a graph like this. I didn't quite get it done. But the contention is that the only thing that's special in this nanomaterial is simply that you've localized, you reduce the distance from your active sites to a place where you can get the helium. Okay.
So getting the helium out is more important than getting it to load quickly, or?
No, you're asking about relative importance. But the goal here is to try to get some understanding of what the heck is going on. Once you know what's going on, then if you're doing engineering, you can lay out the different parameters. Say, well, I want to make this many vacancies. I want to load it this way to make my D2. When it gets going, I want to arrange to get the helium out. Maybe I've got some other tricks to get the helium out faster, and so forth and so forth. Okay, so observed temperature dependence is consistent with helium diffusion. Not a proof that that's what's responsible for the temperature dependence. Has been pointed out to me again, which I agree with. I mean, we need more experiments. We really need to be sure that this is what's going on. Propose that helium fills up the vacancy sites. It's limiting excess power. Consistency with active vacancy sites being at the outside of the cathode in many experiments. If you build either through co-deposition or nanoconstruction or other construction layers, if you made construction with different amounts of thicknesses, you saw excess power and you had a time result helium measurement, then you could correlate the helium leak time with the layer thickness. And then you'd really be sure of what's going on. It would be really nice to have some experiments that really zero in and double check that. Again, there are no resources in this field to do any of this. So this is my wish list to Santa. I'll be as good as I'm capable of, which my wife tells me isn't particularly good. But maybe Santa will get me some experimental results. And scaling favorable for application at elevated temperatures, which is really interesting because people are interested in this technology and operating at the elevated temperatures. Of course, the elevated temperatures can be deuterium or hydrogen can be problematic. Takeaway message time. Drill. Questions, comments, more questions, more thoughts, more comments. Okay. All right, now we're going to begin in the general direction of theory. And before we get to theory, we've got some more experiments to wrestle with, but we need some theoretical concepts. Rutherford, one of the more famous electrical engineers in the nuclear physics business, New Zealander. Rutherford's famous for the billiard ball picture for nuclear physics. So the idea is some experiments were done, alpha particles hit a gold foil, and they got large angle deflections. The interpretation of that was alpha particle nuclei hitting the nucleus of atoms and having a hardcore interaction and bouncing. From my perspective, what's most interesting about this relevant to the discussion here is the billiard ball picture itself. And in the billiard ball picture, you can visualize the balls one hits another. During a collision event, the output is consistent with conservation of energy and momentum. And from the time of Rutherford, this Rutherford picture of local conservation of energy and momentum on a microscopic scale has been a cornerstone of nuclear physics. And I'm not gonna try to shake this particular cornerstone. This is a good cornerstone. So as a result, you can do a calculation where you take the initial momenta, the final state momenta, the initial energy, the final energy, And if you've got like a DD fusion reaction and you're making energy, you can put the energy that you make here, and you combine these equations, and you can get relationships for the energy as a function of the energy that you make. So this basically simple Rutherford picture can be, you can take advantage of it to understand an awful lot about the kinematics microscopically. So for example, if you've got a DD reaction and you make 3 plus 1, then these relationships can tell you how much energy the one has and how much energy the 3 has. So if you calculate that, you can conclude that for a 2 plus 2, 2 deuterons coming in going to 3 plus 1, that the 1 ought to get 3/4 of the energy, and the 3 ought to get 1/4 of the energy, with the energies divvied up, in this particular case, of an inverse mass. So, if you like, Rutherford's ideas and notions here are very useful, and we should be able to make use of it in order to start understanding something about what's happening in Fleisch-Pons experiment. So let me give you an example of the discussion. Imagine for a moment, as was proposed back in early times, and this keeps being proposed again and again and again. And actually, at this point, such a proposal is described in no less than Physical Review, I think A these days. So in this case, I imagine 2 deuterons somehow come together, somehow react to make helium-4, and push off of what I'll call X here. And X might be a palladium nucleus, it might be an electron, it might be a deuteron, it might be a proton, it might be something. Who knows what it is? Anyway, we're going to have to look at some experimental data before we can figure out what we're pushing off against. However, the same basic idea works. Namely, you've got some bodies coming together, you've got some bodies pushing apart, and the energy of the final state products is going to be divvied up non-relativistically according to the inverse mass. So the idea is that if we can measure the energy of this guy, that's going to tell us what this guy was. And if we know what this guy was, then we're going to be in much better shape trying to sort out what the reaction is, what's going on. Okay, so takeaway message, Rutherford picture. We got this billiard ball type picture. We got local conservation energy and momentum. And we can use that to set up a calculation that says if we can measure the helium-4, the alpha particle energy, then we would learn something about what's going on microscopically in the reaction. Takeaway message, questions, comments so far? All right, so how do we measure the helium-4 energy, the alpha particle energy? So we've argued that if 2 deuterons come together and make helium-4, the mass difference energy is basically 24 MeV. If we had a reaction, something like DD, going to helium-4 near another body, then we're going to be able to figure out the mass of the other body if we can measure the helium-4 energy. So to measure the helium-4 energy, well, we have a number of tools. We can use silicon surface barriers. We can use emulsion detectors. We can use scintillators. We covered normal nuclear techniques. Basically require the detector to be somewhere close enough to get the alpha particle. If the alpha particle is born in the cathode, then it's going to lose some energy in the cathode, and it's going to lose some energy in the water. Plus, if you talk to the electrochemists about putting a big detector into their electrolyte, you're going to hear them scream because it perturbs the electrochemistry significantly. So if you like, what we need is we need some new kind of idea as to how to do this detection. Now, my thought on this was to have the palladium deuteride be the detector. The alpha particles born in the palladium deuteride. why not use the palladium deuteride for nuclear detection? I mean, it's not your average nuclear detector. I'll grant you that. It's not a silicon surface barrier detector or simulator CR39 or anything. But it is a detector. And as it turns out, after you think about it and analyze it and so forth, it turns out to be an exquisitely sensitive detector. In fact, you might argue it's the perfect detector. So the argument then is if you've got an alpha particle that's born, and conceptually, when it's born inside, but conceptually you think of it as coming in and hitting this detector, then what's it going to do? Well, it can scatter off of the palladium. There's deuterons inside. If an alpha particle hits a deuteron, an alpha particle, if it's got enough energy, could shatter the deuteron. If it doesn't have enough energy, it can hit a deuteron. And now the deuteron's got the energy. And if the deuteron has the energy, you can have a subsequent deuteron fusion. So you can, if you calibrate this, you can use it as, like I said, an exquisitely sensitive nuclear detector.
Well, what's the output though? Detected output.
But if you shatter a deuteron, you get a neutron that's long range.
So you
And
measure
if you have a DD fusion reaction, half the time you get a neutron, which you can measure. So if you measure neutrons outside the cell, then that tells you something about the energy that the alpha was pulling out.
Okay.
So to calibrate the detector, the range data, the energy loss data for alpha particles in palladium or palladium deuteride can be calculated with the trim code now, SRIM, Ziegler's code. The range looks like this. If your alphas have an MEV, it goes, I don't know, a micron and a half or so palladium deuteride. If it's got 10 MEV, it goes 20 microns in palladium deuteride. It turns out you can do this also for D2O. I guess there it is. So qualitatively, it's similar. So you can do calibration calculations for D2O. You can do calibration calculations for palladium deuteride. If you're near the surface, you have to go one way, you have to go the other way. Here's the yield that you'd expect from the breakup reaction. So here an alpha particle is destroying the deuteron and making a neutron proton coming up. To get this to work, you need, I don't know, 8, 9, 10 MeV. But the yield is very high. So I made the yield in terms of neutrons per joule because you can measure the number of neutrons per joule. And numbers here, 10 to the 5th, 10 to the 6th. Basically, that's a lot of neutrons per joule, easily measured. But what's more interesting, and as I said, this as a detector, palladium deuteride is explicit for this application. These are calculated curves for secondary neutron production. So an alpha particle hits a deuteron, the deuteron hits another deuteron, you get a DD fusion reaction. So this curve assumes a screening energy. And people do low energy beam experiments. And the yield for DD fusion is consistent with some local screening. And the most screening anyone's ever seen corresponds to screening energy of about 800 electron volts. Between 250 and 450, this one's 400 electron volts. So the blue line here is probably the closest to the right answer. The black line assumes the 25 volt screening, which you see for deuteron hitting deuterated plastic or deuterium gas. So what you see is that in the range of 10 kilovolts, 20 kilovolts, if you get even 1 neutron per joule, then if the alpha particle has at least 10 keV, then you're going to get enough neutrons that you've got a chance to see. So as an alpha detector, palladium deuteride is superb.
But you are indirectly measuring neutrons, right? or you're measuring the neutron output from the,
neutrons can be measured. They can get out of the cell. They
Right.
don't do much in the way of energy loss between the cell.
then you have to use some CR39 or something to detect
Well,
these
people have
neutrons.
done much better than CR39. They've used real neutron detectors. I'll show.
They cost a lot of money.
They do.
See, I'm practical. I want to use the CR39.
Okay, so Palladium theodrite very sensitive. Alpha range is good. We can see the sensitivity of the detector goes down to sensibly to 10 keV. We can detect neutrons outside the cell, and D2O is qualitatively similar to palladium deuteron. So let me look at some experimental results. Here's some results that were published by Takahashi. Takahashi at that time had a big group and had substantial funding. Is it Osaka in this case? I'm not sure I remember. Anyway, Takahashi introduced a protocol for experiments where he had a low-high protocol. He'd run high current density and then he'd run low current density and then run high current density and run low current density. And back in those days, sort of my thinking was that different things happen in different regimes. For example, excess heat would be seen in a high current regime. So if you were at 250 to 500 milliamps per square centimeter in a Flesch-Plotz cathode, you would maximize your chance of seeing excess heat. And tritium would be seen somewhere near 70 milliamps per square centimeter. Neutron production would be correlated with a current density closer between 5 and 20 milliamps per square centimeter. So the thought here, namely, Takahashi wasn't thinking the same way that I was just describing thinking, but the idea is that if you do high current regime and low current regime, then looking at energy and looking for neutrons, retrospectively, what might be interesting is to look for the low current density regime and see if you get lots of neutrons. Look at the high current density regime and see if you get excess heat. And there have been some studies devoted towards that, and there seems to be a correlation of that sort that's real. But in this experiment, so here's high current mode excess heat, here's low current mode lack of excess heat, here's high current mode excess heat, here's low current mode lack of excess heat, here's excess power, so here's 100 watts. So this is a big high power kind of system. And if you like a big high power kind of system, it's exactly what you need if you want to maximize the number of neutrons out and get a good measurement. Takahashi had several neutron detectors. I don't remember what is a Helium 3 detector anymore. I have to go back and look at the paper and remember what kind of detector
And
it is.
what is his high current level? How many milliamps, amps?
Well, it's amps per square centimeter. High current density. I don't remember. I have to go back and look. But typically, a number like 500 milliamps per square centimeter for this would be a high current density regime, and low current density would be 10 to 30 milliamps per square centimeter. So anyway, excess power. I don't see a corresponding big burst of neutrons. 100 watts of excess power. I don't know. Is this a corresponding big burst of neutrons? It sort of looks similar to the others. So this is one example of data. There were roughly, 10 to 12 data sets that had reports of excess heat in connection with neutron measurements. And in general, there was no correlation between neutron emission and excess heat. Let me show you the results. So there were a smaller number that gave enough parameters, numbers for detectors and efficiency and so forth. I was able to back out an upper limit for the yield in terms of neutrons per joule. And Takahashi would be right here. And from Takahashi's data, you can infer something in the neighborhood of an upper limit of 1 neutron per every 100 joules. And 1 neutron per every 100 joules would correspond to this point, would correspond to an upper limit of about 8 keV. The conclusion from this is actually interesting. Namely, the mass difference between D2 and helium-4 is 24 MeV. But we know from the experimental results now that the alpha particle, the helium-4, is born with an energy, conservatively less than 20 keV. It's less than 1 part in 1,000 of the reaction energy. And for those of you who were knowledgeable about nuclear physics and so forth, this is shocking. This is nothing less than shocking. So let's look at candidate reactions. Suppose, as has been proposed, 2 deuterons come together and make helium-4 push off of palladium. Then the alpha particle energy would be expected to have 23 MeV. That's ruled out by 10 orders of magnitude. So we can be absolutely sure that's not what's happening. You can push off of a deuteron, and now you're down to 8 MeV. Well, we're sure that's not happening also, because if that's what was going on, we would get like 6 or 8 orders of magnitude more neutrons. You could say, well, 2 deuterons pushing off an electron, now the alpha particle energy is down to 76 kilovolts. Much better, but that's ruled out by at least 2 orders of magnitude for the neutron part, to say nothing about having a wad of 24 MeV electrons, which would be a pretty exciting thing to behold. So as a result, in the I do PowerPoint, I start with a picture of Rutherford. I go through these reactions, I click the button, and then the cross shows up, so Rutherford gets X'd out. But our conclusion is that there is simply no, there are no simple Rutherford picture reactions that are consistent with experiment. And not just no simple Rutherford reaction. You can say, well, what's the first Rutherford type reaction which is consistent with experiment? And along those lines, one of my colleagues, Kim, in connection with these kinds of arguments, he said, well, in his theory, one reaction happens, 2 Ds come together, and makes a helium-4, and the energy is spread out among 25,000 deuterons. So that's your first Rutherford-style reaction that would be consistent with these experiments. For my nickel, I don't think it can work that way. Okay, so here's the argument. We can learn something about that reaction microscopically by measuring the alpha energy. Hard to use detectors, but we can make palladium deuteride Beer detector. We can also make D2O Beer detector. Exquisite detectors, we calibrate it, so theoretical calibration has been established. We conclude that the alpha particle is born essentially standing still. Namely, this is consistent with the 2 Ds coming together, making an alpha, and the alpha sitting in the same place. This is essentially, from a nuclear perspective, this is basically that the helium-4 is born stationary. Not on the G graph. There's another set of experiments that I might refer to here. There are experiments in which tritium is produced, and an expert in neutron detection, Kevin Wolf, teamed up with one of my friends from Los Alamos, Tom Claytor. And Tom Claytor is doing experiments in which tritium, substantial amounts of tritium was being made. And Kevin Wolf challenged him to make the tritium be witnessed by his super-sensitive neutron detection system. And the experiment was done. Later said, well, here's the tritium. I made all kinds of tritium. And Wolf looked at his detector, and there were no detectable DT neutrons. And Wolf placed an upper limit on the triton energy at around 8 keV from those experiments. which is sort of the same number as for the alpha particle in using. And in both cases, there are upper limits. We don't have a positive measurement for what energy it is, but we know for sure that it's got to be less than something in the neighborhood of 8, 10, 20 keV.
It sounds like you're saying these alphas have no momentum.
Right.
Ultra low momentum neutrons, are we talking about the same thing?
This is consistent with the alphas being born just sitting there like a rock in the same place that the 2Ds.
That sounds like the Witten-Larson theory of ultra low momentum neutrons being born.
That is not the conclusion that I would come to. And I think that this argument that Witten-Larson would object to the notion of their theory being ascribed to any of the arguments being put forth here.
Okay.
Other comments or thoughts? Okay. I want to talk a little bit about the two laser experiment in connection with this argument. Okay, so time to step back and think a bit. And in order to think, I have Calvin and Hobbes here to help me with my thinking. So get lots of energy. We see helium-4 correlated with the excess power. We get a reaction Q value, which appears to be consistent with TV going helium-4. It doesn't prove that that's what's going on, but we have, from two of the best experiments, we have consistency. So if helium is a reaction product, the helium is born at rest, and there is no commensurate nuclear radiation. No plausible Rutherford reaction consistent with experiment. So a rational question is, where in the world is the energy going? Namely, if you got two deuterons coming together making helium-4, normally you get a gamma coming out. There's no way to hide or block or convert the gamma, and the gamma is just simply not there. So where is the energy going? And if you like, I'm sort of asking this not quite yet as a theorist, I'm asking this sort of from an experimental perspective. The energy is going somewhere, and you want to know where it's going, you've got to go and you've got to measure it. And that's not easy. So let me sort of frame the question at a high level. I'm going to look down on it. So the experimental results seem to be consistent with something like this. If the energy goes into nuclear degrees of freedom, then I'd expect to see gamma now, because that's what you normally get for this reaction. However, Fleisch and Pons is doing something new. Fleisch and Pons did not read the nuclear physics textbooks or condensed matter textbooks, so it's not behaving in a way that we know something about. So perhaps the energy is going into condensed matter degrees of freedom, maybe. Namely, new experiment, new physical effect, looking at it and saying, what the heck's going on? Here's a conjecture. Either it goes that way or it goes this way. We sort of know that it's not going that way. No energetic nuclear radiation, no gammas, no nothing that's we normally associate with a nuclear reaction. Maybe it's doing something new. Maybe the energy is going into some condensed matter degree free. So can we phrase the argument this way? And this brings us to work of Letts and Craven on laser-induced excess heat. And the way it started is that Cravens and Letts noticed that by shining a laser, a laser pointer, and then they moved to diode lasers. Yes, they will. Laser pointer is a diode laser. Well, yes, okay. So they have diode lasers that hit the surface of a Fleisch and Pons cathode. And as I remarked the other day, the cathode is running under conditions where the gain's been turned down for excess heat. So excess heat, you get more of it, and the threshold's improved if you raise the temperature. If you get more current density, then it's easier to get excess heat. So if you don't want there to be excess heat, you back off on the current density, back off on the temperature, and the idea is that if you come in with a laser, then maybe the laser makes the excess heat turn on. So here's an example. This looks like LETS. Yeah, I think this is an example from a LETS experiment where no excess heat, so one temperature, single laser is turned on, temperature comes up. This is the basic effect. They got this result, and a lot of other people tried it out. Mitchell tried it, SRI tried it, Storms tried it, and they saw the effect. And if Scotty tried it, they saw the effect as well. Here's an example of the effect at SRI. Let me look at this guy right here. So there's no laser turning on. Here the laser turns on, and this is the temperature that the laser diode's running at. Now scanning the temperature scans the wavelength. There's a question as to which wavelength is most sensitive. And scanning the wavelength in connection with it, there seems to be an excess power event here. I can't even read. This looks like milliwatts. This looks like 150 milliwatts. And then when the laser turns off, the excess power goes away. As an example, these guys right here, this is where gold plating goes in. And LETS would swear by gold plating. And I say, well, what in the world does this little bit of gold do? Well, it turns out, if you go and you look in the literature, you find that a thin layer of gold has a plasma resonance that's reasonably well matched to red light. And for example, in this case, here's the laser turning on and scanning. Here's the event, largest event, 250 milliwatts. When the laser turns off, then things start coming down. So this is the basic a replication of the basic effect. And one of the things that was really interesting to me about these experiments was that this was one of the first examples of control. You might say this really isn't control, but if you look here, you turn the laser on, excess heat goes on. You turn the laser off, excess heat goes off. The laser power is much lower than the excess heat that's resulting from it. It's like a little bit like a switch. You turn it on, you turn it off. I view this as being a really important result. I mean, having excess heat wants to come on, turn off, but it wants to come off. That's like inconvenient. I know it's like you turn it on, I can turn it off.
I think you just answered my question. It was whether or not that was calibrated for the laser energy to the excess heat energy being put out on that scale.
This effect was observed with laser powers between like 1 milliwatt and 30 milliwatts or so, and not all the light gets absorbed. In this case, the excess power is incremental excess power is over 200 milliwatts.
So it's much greater.
It can be a big effect.
Were you implying that there was a tunable laser, so different wavelengths stepping up there?
Yeah, these lasers scan different wavelengths. And I know from the results here, there's evidence in these experiments, there's evidence in other experiments that the effect actually is sensitive to the wavelength, that there's a wavelength that it's happiest with.